Hi, my name is Gigi Rill, and I'm president for Rice Electric Vehicle for the 2017-2018 school year. Rice Electric Vehicle, or REV for short, is a competitive undergraduate engineering team at Rice University in Houston, Texas. What we do is provide engineers with a hands-on learning experience in their undergraduate years and compete in the Shell Eco Marathon Americas division this upcoming spring. What we're going to do in this video is give you a brief introduction to the car, working through both the electrical and mechanical systems. Let's start with a tour. This is the car. It's currently under a state of construction, considering we're tearing everything apart and rebuilding and machining things. But this is the front of the car. It's made out of carbon fiber, and this is our cockpit. It has a 5-point harness in the middle, and it's got our steering wheel and our side opening door. We have our windshield wiper, and we will eventually have a dashboard up in the front. This is the rear of our car. We currently don't have anything in it right now, considering we are currently machining all of the parts as well as working with the electrical systems. But this is the wheel well. It's where the motor and the wheel will be situated. The motor is going to be connected to a gear train system in here, connected to the wheel. Up here will be where our battery and motor controller are located.
Hello, my name is Manuel Pacheco, and I'm the Chief Engineer of Rice Electric Vehicle. Today I'll be talking to you about our general circuitry, including our battery and its protection systems. So, in general, the way it works is that we have a 48-volt lithium-ion battery, which can be seen here. It is made by ALSO, which manufactures batteries. It's a 48-volt lithium-ion battery, 1,000 watt-hours, which is within the allowed range. It's connected via a 50-amp fuse here, and features Anderson SP50 power connectors, as you see there. And then from the 50-amp fuse, we come down to the motor controller. The motor controller can be seen here, which also interfaces with Anderson SP50 connectors. It features 2 MOSFETs, which control the speed of each motor. We have 2 motors. And my colleague Irene will go more in detail about the motor controller in a later video. From the motor controller, we also have the 48-volt rail that comes down to the buck converter, which outputs a 12 volts out to the auxiliary system. So here's our buck converter. It inputs 48 volts, and then it outputs about 12 volts. You can set it by the potentiometer here. This is something we bought, and we'll be able to use it to power up things such as a horn, and the light, and the blinkers, and the windshield wiper, things like that. The lights that we use are just LED strips, such as these. These LED strips are a good bright color. We tape them to the front of our car. They're pretty bright, and they're also weather resistant. They're waterproof. As you can see, they have a silicone protection layer on top to protect against water moisture. Furthermore, our battery is made by ALSO. It's professionally manufactured. It's very safe. It features a battery management system. We can see more of the specifics here. So it protects against voltage, overcurrent, overcharge protection, overcurrent protection, short protection, resistance, temperature, etc. And this is a schematic, I think, of the battery management system, the BMS that's inside of our battery. This was documentation provided by ALSO.
Hello, so I'm going to give you an overview of our current motor controller. So this is our motor controller PCB right here. We have 3 Anderson connectors that go to the motor controller. This goes to battery, and these 2 go to the 2 DC brushed motors. We have an Arduino and pedal that outputs a PWM signal to the gate of our 2 MOSFETs. We have 2 LED indicator lights here that tell us how much duty cycle we're producing from the PWM. And by changing the duty cycle of the PWM, we're able to change the current that's flowing between the source and the drain of the MOSFET. And the same current will be fed into the 2 motors. Therefore, when we change the duty cycle of our PWM, we're controlling the speed of the motor. And we also have some additional safety features on our board. So we have the 2 diodes here, And the two diodes are placed between the source of the MOSFET and our Arduino. Whenever there's a huge voltage buildup at the source of the MOSFET, these diodes will redirect the current back to the motor so that our Arduino will not be damaged. And we also have two resistors here that's connected between the source and the ground. These resistors allow us to test the current that's flowing through the motor. And this allows us to get a better idea of the amount of current that's flowing through the motor.
So we calculated that we needed a 1:5 gear ratio at minimum. So how we achieved that was we had the 11 tooth sprocket from the motor go to a 44 tooth sprocket on an intermediate axis and then axle, and then we took a 20 tooth sprocket and then linked it by another chain to the 28 tooth sprocket on the wheel axle. That's where the wheel is, that's where the motor is, and that's shown here. I'm showing this in a video form right now because we're doing some remachining on the parts. So this is currently not functioning. Here's the motor with the 11 tooth sprocket, the 44 tooth sprocket, the 20 tooth sprocket, and the wheel axle, which has the 28 tooth sprocket. As you can see, there's two loops of chain to achieve the multiplying gear ratio. Let me show that too.
Now moving on to the other side of the chassis wall. Previously we described how the drivetrain transmit torque to the sprocket, which will be on this side. Then the chassis wall will go here. This is our suspension block. We were having a problem with our suspension where the shaft and wheel combination would move kind of towards the middle of the car. So we remedied that by putting these new tapered bearings in, which should prevent the axle from moving in and out while the car is in motion. This long piece here we call the end cap, which is where we will attach our go-kart disc caliper. In this middle space here is where the disc brake will actually go, and then this is our wheel. We leave these holes. We don't have holes here yet because we're going to determine where the disc caliper should go once we set up the whole back suspension. Last year we had bike brakes, and after the rules were changed this year to require brakes that were not bike brakes, we acquired these hydraulic go-kart brakes. These were acquired from an online vendor and go along with these 3mm discs. Because our axle wouldn't fit the 3mm discs, we had to machine these adapter plates to adjust the disc down to the size of the shaft.
So this is our steering wheel, and then it connects to this steering shaft, which connects to this machine anchor looking piece, which pushes on both ends of the front suspension to turn the wheels.
For the auxiliary circuits of our car, we have a buck converter that will step down the 48 volts that we get from our battery to 12 volts for all the auxiliary components to run on. This is our dashboard control unit. It has switches to control each of the auxiliary components, which include the headlights, the left and right turn signals, the hazard lights, the horn, and the windshield wiper. The left and right turn signals and the hazard lights all run off of 555 timer circuits, which take an input voltage and output an oscillating voltage to turn the lights on and off.
That wraps up our video. If you'd like to learn more about Rice Electric Vehicle, please visit us on our website, revteam.blogs.rice.edu. Thanks!